Hey, this is Dr. Berang. I am in mechanical engineering faculty. I'm also a licensed professional engineer in the area of thermofluids in the state of Washington. This video is about reheat Rankine cycle. We're going to solve the ideal cycle. I decided to make this video because in one of the comments of one of my previous videos, it was the regular ideal Rankine cycle that somebody asked for the reheat cycle. So I decided to make a video about it. Before I start, make sure you subscribe to this channel as I upload more videos in the area of thermofluids. Let's get to it. So the reheat cycle, the reason that we have the reheat cycle is if you can read the theory about it, but this is just the whole thing, that if you increase the average temperature of the fluid in the cycle, or in general, if you create more distance between the average high temperature in the cycle and the average low temperature in the cycle, basically you can increase the efficiency of the cycle. So that's the main reason behind reheating the cycle. And the same thing for regenerative cycles. We have a different one. We can have a combination of reheat and regenerative. So maybe I'll make a video about the regenerative cycle later, but this one is about reheat cycle. So let's take a look at the ideal reheat cycle and how we can analyze it. Then I'm going to point out a couple of things about the pumps and the turbine and how to calculate the efficiency of it. And we're going to write a complete code in EES, Engineering Equation Solver, to be able to solve this cycle. I will also mention how to solve it by hand very quickly. So if you want to solve it by hand, you can do it. And in this video, we're going to look at example 10-4 of Cengel's Thermodynamics book. So the solution is also in the book. So I'm going to solve it with EES, but the solution by hand is in the book. Let's do it. So let's take a look at the cycle and the TS diagram of it first. And let's see how that works. So before you watch this video, I expect you to know how the Rankine cycle works, right? I expect you to know the first law of thermodynamics and the second law of thermodynamics. So if you're not familiar with the Rankine cycle, I suggest that you go watch the video I posted about ideal Rankine cycle. I'll post a link in the description for you. And basically, you'll be fine. You can come back here and watch this video. So this is the reheat cycle. As you can see here, there are 2 points here, point 5 and point 3, that as opposed to a regular ideal Rankine cycle, that when the steam goes into the turbine, you get the work out of it and it directly goes to the condenser. Here, what you can see here, the steam goes into the high pressure turbine, comes out, so you can get some work out of it. That would be W dot of turbine number 1, high pressure. And then it goes back into the boiler and gets reheated, because this is an ideal cycle, almost to the same temperature, according to this graph that we have here, almost the same temperature. So this tells me that T5 and T3 are supposed to be the same temperature. And then it goes back into the low pressure turbine, as we can see here, and we get some more work out of it. That would be W dot turbine number 2, and then it goes into the condenser. So one more time, after it goes to a high pressure turbine, we get some work out of it. Then it comes out, it goes to the boiler, it gets reheated at a lower pressure because the turbine, lowered the pressure of it because it got some work out of it, right? So then it goes back to the low pressure turbine, and then we get some work out of it. And when it comes out at state 6 here, basically it has lower pressure, maybe 10 kPa, maybe 25 kPa. These are the range of the pressures for Rankine cycle for the condenser, right? So now let's go over the cycle very quickly, and then we're going to look at that example. So let me just get rid of these and start over. So let's start with state 1. State 1, because it's an ideal Rankine cycle, so state 1 is a state that it's supposed to be saturated liquid. So quality here is supposed to be 0, right? So X1 is basically 0, and this is just saturated liquid. It goes through the pump. When it comes out of the pump, basically, if this is an ideal cycle, For an ideal cycle, the pump and the turbine is supposed to be isentropic. There are some, and if you're, you have a piece of paper, you can write these things down. When it comes to ideal cycle, basically there are some conditions that we need to take a look at. The ideal cycle, the first condition is that, the pumps and the turbines, are supposed to be isentropic. What does isentropic mean? Well, I expect you to know, but isentropic means adiabatic and reversible. In other words, the entropy doesn't change across the pump or across the turbine when it goes to the turbine or the pump, right? And also you assume that the heat exchangers are perfect. Heat exchangers are perfect means that, what does that mean? It means there is no pressure loss in the heat exchanger. There's also no pressure loss in the piping. So, none of these pipes that you can see here have pressure loss. There's no pressure loss in the condenser, no pressure loss in the boiler. And normally, when the problem doesn't say anything, if it is an ideal cycle, that temperature T5 is supposed to be temperature T3, because if it is a perfect heat exchanger, then it's going to heat up the fluid to the same maximum temperature that T3 was at the beginning, right? So again, if you're familiar with the regular ideal Rankine cycle, you get what's going on here. But let's go through it. So what we have here at state 1, let's see what you usually know. Quality is 0 there. Then state 2, because the pump is isentropic, S2 is supposed to be S1. And because of that, we can see a vertical line here. That's a vertical line from 1 to 2 on the TS diagram, because S2 is supposed to be S1. Why? Because it's an isentropic pump. Entropy doesn't change. Then on a constant pressure process, why do we call it constant pressure process? Because we say it's an ideal cycle. So there is no pressure loss in the boiler or in the piping, right? So the pressure at 2 here, what you see here is the same pressure at 3. This line that you see here, this pink line here, you see it's a constant pressure line that water is just getting heated on this constant pressure line. So it goes through the boiler. It comes out of this side of the boiler, becomes state 3. So, and there is some, we provided the boiler gives the, basically Q dot of boiler is happening here, that, the boiler gives the fluid, heat, right? It goes through the turbine. This is where the pressure and P3 is basically the maximum pressure in the cycle, and T3 is also the maximum temperature in the cycle. So it goes through the turbine, and then of course we get the first work, power, W dot turbine 1, because from the high pressure turbine, it comes out at a lower pressure. And let's look at it at the TS diagram. When you look at the TS diagram, you can see that S3 again here, because it's an isentropic turbine, S4 is supposed to be S3. And you can see another vertical line here, 3 and 4, it's a vertical line because it's isentropic, it's an isentropic turbine. And then it goes into the boiler again, and because it's an ideal cycle, pressure 4 and pressure 5 are supposed to be the same, basically. Let me just write it in a way that it's obvious. P4 is supposed to be P5, like this, because again, that's a constant pressure line where this is getting heated up. It goes to state 5 again, when the problem doesn't say anything. If it's an ideal cycle, we assume that T3 and T5 are the same. So if it was a perfect heat exchanger, then the fluid it got heated again to the same level as T3, basically. And that's the maximum heat that you could give it, maximum temperature that it could reach, basically. Okay, so it comes out here, and you can see here it says, P4 and P5 are the same. So now it goes into the low pressure turbine. Again, because the turbines are isentropic, this tells me that S5 and S6 have to be the same. And you can see it here, S6 is supposed to be S5, basically, and you get some work out of it, W dot turbine number 2, and it eventually goes to the condenser. In the condenser state 6, usually there is a quality here, like that's quality X, somewhere between 0 and 1, basically, usually 80%, 90%, whatever that is. And then it goes through the condenser, and of course, P6 is supposed to be P1, because again, there's not supposed to be any pressure loss in the condenser. So that's the general picture. And if you want to calculate the efficiency of the cycle, I'm going to write the equations on the next page because it got kind of crowded here. But this is how the TS diagram works. And if you want to, the pieces of information that you need to solve a problem like this looks like that I just need to know basically two pressures. Basically three pressures when you think about it. You need the pressure at state 1, you need the pressure at state 2, you need pressure at state 4, right? So I need this pressure here, pressure 1. I need this pressure here, pressure 2, pressure 3 is the same. I need the low pressure turbine, and of course, I need the temperature here at state 3. So looks like if it's an ideal cycle, if you have these four pieces of information, which means P1, P2, P4, and T3. If I know these four pieces of information, I can solve the whole cycle because it's supposed to be ideal. There is no pressure loss. All the pumps are isentropic. What does that mean? It means the efficiency of the pump is 100%. Even if it's not 100%, you can still solve it. I mean, I have a video over like 40 minutes about how to solve the pump work when it is not an ideal pump. You can watch that video for the cases that the efficiency of the pump is not 100%. For this case, the efficiency of the pump is 100%. So if I want to actually write it here, the efficiency of the pump, the isentropic efficiency of the pump, I have to say, is 100%. Same case with the isentropic efficiency of these turbines. So the isentropic efficiency of the pump is 100%, and the isentropic efficiency of the turbines, 1 and 2, both of them are basically 100%. So that's what it means. Now, let's take a look at an example to see what we can do to solve this problem. Before we look at the example, I'm going to explain how to solve the cycle and find the efficiency of it. I guess that's what we need. But let's take a look at the example first, and then we go from there, basically. So this is the example. This is example 10-4 from Cengel's book. And so, you can pause this video and take a look at the example. Or I'm going to go through the example, but if you want to pause the video, go ahead and do it so you can read the example. It says we have a steam power plant. Okay, sure, it's an ideal. Look at this. It says ideal reheat Rankine cycle. These two terms are important. It gives you the value of maximum pressure. I can see this 15 megapascal and 600 Celsius, which means that P3, which is supposed to be P2, I already know because it's an ideal cycle, right? It's supposed to be 15 megapascal. And T3 is supposed to be 600 Celsius. Because it doesn't say anything else in the problem about state 5, I have to assume, because it doesn't say anything, it's a perfect cycle, I have to assume that T5 is also same as T3 and it's supposed to be 600 degrees Celsius because it didn't say anything. The value of P1 is given. P1 is 10 kPa, right? So as I said before, we need 4 pieces of information. So how many pieces of information do I have? I have actually 3. I have 2 pressures and 1 temperature. I either need to have the value of P4, right, or something else. So let's read the problem. Okay, so it says it's condenser, the condenser pressure is given as 10 kPa. I can see it here, and it says if the moisture content of the steam at the exit of the low pressure turbine is not to exceed 10.4%, then solve this cycle, which means to look for the efficiency of the cycle, and it in fact wants you to find that P4. So P4 is not given, something else is given in this problem. What is that something else? The quality X6 is in fact given. What is X6? It says the moisture is not supposed to exceed 10.4%, which means X6 is 100% minus 10.4%, being basically 89.6%, right? That's what it means. So in other words, X6 would be, if you want to enter EES, that would be 0.896. So now I have 4 pieces of information. I can solve this cycle. So remember, to solve an ideal, regular ideal Rankine cycle, you need basically only 3 pieces of information. You need the low pressure, you need the high pressure, you need the high temperature. To solve ideal reheat cycle with only 1 reheat, so we can have multiple reheats, by the way. That's a different story. This problem has only 1 reheat with 2, 2 stages of, turbines. So if that's the case, you need 4 pieces of information. If we wanted to reheat this, the steam multiple times, you needed more pieces of information, basically. But for this cycle, 4 and 4 is given, so this problem can be solved. Okay, now let's take a look at how we can actually solve this problem. Let's go through the steps and what laws do we need to apply on this cycle, and then eventually we get to the EES code and we get it done. Let's look at that. Okay, so we need to, look at the equations. When you want to solve this problem, the best way to solve any of these problems is to determine the states. If you somehow figure out how to determine every state, you are good to go. You can solve the cycle. And by state, there are usually 2 or 3 pieces of information that you need to find for every state. Normally, you need to know the pressure at that state. If you want to do the TS diagram, you need the temperature. You need the enthalpy, because you need enthalpy shows up everywhere in the first law, right? And you need entropy. So there's P, T, H, and S, right? So let's write it down so we know what we are looking for. For every state, I need to know what is pressure, what is temperature, what is entropy, and what is enthalpy. So if I somehow know these values, I should be good to go. I can solve the cycle. So let's see if we have enough information for every state. So we're going to go through the states one by one. So state 1, let's take a look at state 1. I want to have the cycle so you can see what this cycle is all about. State 1, what do I know about state 1? State 1, I know the quality is supposed to be 0, and I know the pressure, P1, is given, 10 kPa. If I know these 2, this is saturated liquid. The information is enough. I can go to steam tables. You can either go to EES, right? And we're going to solve this problem by EES, or you can go to steam tables, to saturated liquid, steam tables, right? Pressure table, basically you have to go to pressure tables, right? And then you can find the value of H1, which is basically HF, right? At 10 kPa. You can find it there. And you can find the value of S1 if you need it. And you can find the value of V1, basically, which is VF, if you want to calculate the work of the pump by hand at 10 kPa. That is also one way to do it. And of course, you can find T1, same manner. You can find T1 in this case, and you can find S1. If you want to find all of them, you have the option to find all of them. Now, for state 2, there are 2 ways to find state 2, basically. State 2, the information that I have, if you want to do it by EES, then you need 2 pieces of information. The piece of information is, well, P2 is given. P2 was given to us as 15 megapascal, right? So I have the value. You just have to be careful with the units, because the first one was 10 kPa, this one is 15 megapascal, which means 15,000 kPa. When we write the EES code, we'll take care of it. And S2 is S1 because, you know, it's an isentropic pump. So for ease, this is enough. If you want to do it by hand or steam tables, then you have to do this. H2 equals basically H1 plus V1 times P2 minus P1. I showed over the efficiency of the pump, which in this case would be 100%. So I know that in this case, because it's an, I just write it here, efficiency of the pump is 100%, or just, you can just write 1 basically, because it's an isentropic pump, isentropic efficiency of the pump. It's worth mentioning that it's the isentropic efficiency of the pump. So that's the equation you need to use. And looks like if you want to do it by hand, you know, you have enough information. You might ask, okay, hey, wait a second. So how did you get this equation? You know, H2 is H1 plus V1 times P2 minus P1 over, you know, the isentropic efficiency. I have a video. I can put the link there. You can go watch that video. It's about 40 minutes. So they explain where this equation comes from, right? So that's it. Okay, so it looks like state 2 is determined. Once you have 2 pieces of information, basically you have everything else. Because if I have 2 pieces of information here, I can move this a little bit down so I can actually, let's see what I can do here. Poor job. Let's do one more time. Let's see if I can move this a little bit, just a little bit. Wait, I guess I screwed up. So let's not do that. All right. You know what? I just write it here. So after you have state 2, basically you do have the value of T2 for your ease, and you have the value of P2 that is given. So you have the value of H2, you have the value of P2 that is part of the problem basically, and you have the value of S2. So you are good to go. Basically state 2 is determined, right? Now, what about state 3? So let's take a look at state 3. State 3, what we see here is state 3, in fact, was given by the problem. The problem gave us the value of 15 megapascals and, you know, 600 Celsius. So again, and I hope that you wrote down those numbers. So state 3 is also determined. State 3, there is no problem because we do have the value of T3 and the value of P3. These two are given. Because these two are given, you can either go to ease or you can go to steam tables. You have to go to superheated, right? Superheated tables. And then you can find other properties. You can have the value of S3 if you need to, and you can find the value of H3. These two are determined, state 3 is determined. So let's take a look at what we have here. It looks like these states are determined. State 1 is determined, state 2 is determined, state 3 is determined because every state has 2 pieces of information. What about state 4? What do we know about state 4? So when you look at state 4, we know that S4 is S3. Okay, that's one property. I need one more property. In fact, I don't have it right now. In fact, I'm looking for that pressure. I don't have it. Okay, so just leave it there and let's see what else we have. Then we have state 5. State 5, we know pressure 5 is pressure 4, but I don't have pressure 4. So still, I don't know. What else do I know about state 5? I know something about state 5, that state 5, S5 is supposed to be S6. Okay, so I still don't know what's going on. What about S6? What's going on with S6? When it comes to S6, what is given is I can find the value of S6. Why? Because X6 was given. We know that 89.6%, that is given. And the value of pressure P6 is given. So if I know these two values, I have the value of S6, either from steam tables, I can find it, or you have to find, because you have the quality, and or you can use ease to find S6. If I have S6, I do have the value of S5. So I know the value of S5 in this case. Okay, that's good. Now, if I know the value of S5, because I already knew the value of T5, now this is the interesting part, T5 was supposed to be T3. I know the value of T5. Now state 5 is determined, so its pressure can be found. One more time, because I found S6 from state 6, because the quality and pressure I knew. So I went to the steam table. Basically, this is a two-phase part, so you can go to the saturated water and use the quality, find S6. And then because S5 is S6 and T5 was given, state 5 is determined, so I can find this pressure. I have the pressure at 5, so I have the pressure at 4. Because I knew the entropy at 4, state 4 is also determined. So let's just write it down, have it in writing to organize our thoughts, so we should be good to go. So this is how you kind of back solve it. You start with the state 6, basically. State 6, S6 was given. You can either use EES or steam table. What is steam table? So if I use the steam table, basically S6 is SF at 10 kPa, right? Plus X6 that was given as 0.896 times SFG at 10 kPa if you want to solve it by hand. If you don't want to solve it by hand, use EES. You have two independent properties. I'm going to do it for you, so not a problem. So this way, I got the value of S6. Cool. Now I go to state 5. State 5, because the turbine is isentropic, S5 is S6. Okay, cool. What else did I know about state 5? I knew T5 is T3 is 600 Celsius. I have two independent properties, and this is, you can either use EES or you can go to superheated table, steam table, either, and you can find the value of P5. You can find the value of P5 and you can find the value of H5 if you need it, right? And if you want to do TS diagram, you can, well, you already have S5 anyways. So you have that one. So then state 4 is determined. State 4, because P4 is supposed to be P5, like this, basically, then let's take a look at our cycle. When you look at your cycle, you know this is a high pressure when the turbine. There's something that you need to know, that when you have a high pressure, low pressure turbine, the steam that comes out of the high pressure that comes out of it is still superheated. That's something that you need to know. And if you go back and look at the TS diagram, it was the same thing. But if you don't have the TS diagram, you can write it down that when you are dealing with high pressure then low pressure turbine, when the steam comes out of the high pressure, for sure, it is still superheated, even if you got some work out of it, but still it is superheated. That's something that you need to know. Okay, cool. Now, so I know that state 4 is also superheated. So I have P4. And I somehow happen to have S4. S4 was supposed to be S3. Again, so I have two independent properties here, right? Let me just zoom in. And if I have two independent properties, basically state 4 is also determined. So I can find the value of T4. And I can just say superheated again. Superheated table, right? So you can find the value of H4, because you need to calculate the value of, you need enthalpy to find to apply the first law and find the work from the turbine. H4, and then if you need to find T4, you can find T4 if you need it. Basically, all the states are determined, right? So now if I zoom out, this, let's zoom out so you can see the whole page like this. Basically, you have everything. All 6 states were determined. By determining the state, I mean you have to have those 4 properties, P, T, S, and H. So you have this. If you're solving it by hand, temperature, if you have it, that's great, but it doesn't matter that much because you don't want to do the TS diagram. But if you're doing EES, you want to solve, plot the TS diagram, then yeah, sure. You need to have the temperature. We'll do all of them for you, so you know what's going on. At this point, I already solved the problem because I have the value of pressure. The problem said first give me the pressure at which basically the steam should be reheated. Now, there is a rule of thumb here that you can write down. That's a very important rule of thumb. That the reheat, when it comes to high pressure turbine to low pressure turbine, there's this question that, what would be the range of that pressure, and when it comes to reheat. And the range of the pressure is somewhere around maybe a quarter of the high pressure, somewhere around. It's not exactly that value, right? But in order to maximize the efficiency of the cycle, that would be usually a quarter. We don't know what this pressure is, but I'm guessing that this pressure would be something around, right? So we have maximum pressure, it was 15, a quarter of maximum pressure, that's what I meant. So a quarter of maximum pressure is 15, so a quarter of that would be somewhere around, I don't know, like 4 or 5 megapascals, something like that. 4 or 5 something megapascal, we can calculate. But it's not exact, but it is somewhere there. It's not going to be 1 megapascal. That's my point, right? So if you have like 12 megapascals maximum, maybe the reheat is about 3 megapascals, something like that. But if you have 15, like in this case, maybe it is about 4 megapascals, or something like that. If you divide 15 by 4, you get a value. So it could be probably around 4 or 5 megapascals, something like that. So we'll see what happens. We're going to actually calculate the values of what happens. But that's a rule of thumb. So if you just want to write it down, then generally you expect your answer to be somewhere in that range, right? So that's a good way to remember this. Okay, well, the next step is the problem said, okay, give the efficiency of the cycle. So how do I find the efficiency of the cycle? So let's take a look at the cycle one more time. All right, so we learned about how to find every property at every state. The final equation is the efficiency equation. How do I find the efficiency? Now, the efficiency in general, when we talk about the efficiency of the cycle, is the thermal efficiency is supposed to be some sort of W dot net, right, over the Q dot of boiler. In general, the efficiency is the desired form of energy over the energy spent. So the desired form of energy is obviously the work net that we get out of this whole cycle, and the energy spent is the energy that we provided in the boiler. Basically, that's what it happened, Q dot of boiler. Now, the difference between this case and the regular Rankine cycle is that in this case, we have different streams going in and out of the boiler, as opposed to only 2 streams, we have 4 streams. Let's take a look at this. I have 2 going in, I have 3 coming out, I have 4 going in, and I have 5 coming out. For the case of turbines, I have 3 going in, 4 coming out, 5 going in, and 6 coming out. So it's not just a regular, like a regular cycle, ideal Rankine cycle. It's a little bit, different. So how do I solve this case? For this one, first we have to define what is the W dot net and what is the Q dot of boiler. So W dot net in general, W dot net is the total work done by both turbines, so W turbine total, minus the absolute value of the work consumed by the pump. The reason that I use the absolute value is when you use the first law of thermodynamics, you get a negative value for W dot of the pump because it is consuming power. And Q dot boiler is basically, well, I have to just find it. So let's apply the first law on the turbine, on the boiler, on both turbines, and on the pump. So in order to do that, you have to define some systems, right? So we have to define, let's identify the system that we're going to look at. This is the system for the pump that I'm going to pick, right? And this is the system that I'm going to pick for the boiler. And for turbines, I'm going to, just for efficiency, I am going to pick both turbines in one system. And I'm going to look at what streams are crossing the boundaries of my system. So I have picked 3 different systems: the pump system, the boiler system, and both turbines at the same time. Keep in mind that this cycle is supposed to be ideal, which means that the turbines don't have any Q dot. They're adiabatic, right? So there is no heat loss in the piping system. At the same time, there is no loss in the boiler, so there is no work consumed in the boiler or work produced in the boiler, obviously not. So for the case of the boiler, when you write the first law, there is no W dot. For the case of turbines, when you write the first law, there is no Q dot. For the case of pump, there is no Q dot because the pump is isentropic. So now what you need to do is basically to apply the first law for these 3 cases and find the values what you're looking for. So if you apply the first law for the boiler, basically, you have to look at what streams are crossing the boundaries of the system. Look at the streams that are crossing the boundaries of my system. What you see here is 2 is crossing the boundary, 2 is going in, 3 is coming out, 4 is going in, and 5 is coming out. These 4 streams are crossing the boundaries of my system. So when I apply the total amount of Q dot for boiler, and there is no W dot, so W dot net for the boiler, the net for the whole system is obviously 0 because the boiler is like that. And plus, all these streams have the same M dot, luckily for us. So I can factor out M dot. In some cases, like a regenerative Rankine cycle, then these streams are not the same M dot. There are some mass fractions that you need to take care of. But for this case, all of them are M dot. So that's great. So plus M dot, what is going in? Looking at the boiler, I can see 2 is going in. I'm going to delete it and just do it one more time. So for you guys to see, for the boiler, what's going in is 2 is going in. Okay, so I'm going to write H2. What else is going in? 4 is going in. Okay, so plus H4. What else is going in? Nothing is going in, but something is coming out. What is coming out? I can see 3 is coming out, and I can see 5 is coming out. So that would be minus H3 minus H5, basically equals 0. This equation will give me the value of Q dot of boiler. So this is going to be what you are going to use, basically, right? Now let's do the turbine. For the turbines, you can see that in my system, this is the system that I picked using red color, basically, right? This is the system I picked. So I have to look at how many streams are crossing the boundaries of the system that I picked. For the turbine, so I'm going to write turbines in this case because we have not only 1 turbine, we have 2 of these. So Q dot of turbine is basically both turbines is 0 because they're adiabatic. Minus W dot of turbine total, both of them in this case, because I want to get both of them, plus what all these streams are M dot, luckily for me, so that's great, M dot. What streams are going in? I can see 3 is going in. Okay, great, that's 3 is going in. What else is going in? I can see 5 is going in, crossing the boundaries of my system. Okay, so I'm going to write them. That would be H3 plus H5. These are going into the system. What is crossing the boundary and coming out is basically 4 is coming out, and 5 is, and 4 is coming out, and 6 is coming out. So that would be minus H4, basically, minus H6, like this, equals 0. This is the equation that will give me the power of a turbine. And finally, same case for the pump. What you are going to do for the pump, Q dot of the pump would be basically 0 minus W dot of the pump. And for the pump, you have only 2 streams. 1 is going in and 2 is coming out. So that would be M dot times H1 minus H2, H1 minus H2 equals 0. What we are going to see after solving the problem like this, you realize that W dot of turbine, the total W dot of turbine is going to be a positive number, and the Q dot of boiler, the total is going to be a positive number for sure, but W dot of pump is going to be a negative number, and that's why I use this thing here. So now looking at the whole solution, this is what we are going to apply in our EES code to find the efficiency of the cycle. So the main difference between this one and the regular ideal Rankine cycle, the simple ideal Rankine cycle, is that in the boiler we have 4 streams going in and out, and in the turbines we have 2 turbines, so there are so 4 streams. Since we have only 1 pump, there are only 2 streams going in and out. So that part didn't change. The pump part didn't change, but the other ones changed. So now let's go to EES and write the code from the beginning to the end. So if you know how to use EES, then you can start writing the code with me and check your numbers. If not, if you don't know how to use EES, I have a video that I posted that shows you how to use EES, and you can learn about EES and then come back here and try to do this. So let's get to it and let's do the fun part and write the EES code. Okay, here's EES and engineering equation solver. The fun part begins now, and we're going to write the whole code and solve. And you'll see how quickly we can actually solve a problem like this using parametric tables, not parametric tables, the array tables. And even if you want to plot this TS diagram, you can, but I don't think I need to show it today because I have a separate video that shows how to plot the TS diagram. Again, if you're not familiar with EES, I have a video that shows how EES works. So I put the link in the description, and then you can watch that video and then come back here, see how that works. And if you're familiar with EES and you have EES in front of you, you can start writing the code with me, basically. So what's the first step in EES? The first step in EES is to get the units right. So you have to go to options and then go unit system. So what we have here, you can do Celsius because we had temperatures in Celsius, and we're not doing any ideal gas law or anything, so we need Kelvin. And the pressures are given in kPa, but make sure everything's kPa. The enthalpies are kilojoules per kilogram. I don't have any velocity combined with enthalpy in the first law. So if you have meters per second in the first law and enthalpy, then enthalpy has to be joules per kilogram. You can't combine kilojoules per kilogram with meters per second in the first law. That's not going to work. Since we ignore the changes in potential energy and kinetic energy, I can get away with kilojoules. So I can leave that as kilojoules. However, if I was solving a nozzle problem where velocity and enthalpy are used together, then you have to use joules per kilogram. But not for this problem. For this problem, you can do kilojoules per kilogram, you'll be fine. So let's do Celsius, let's do kilojoules. kPa is fine for us and kilograms. And of course, everything is going to be kilowatts, basically. So the mass flow rate was not given in the problem. So we're going to assume a mass flow rate of 1 kilogram per second. And we just go with that. So the first step is to just, define the given values. The given values is, yes, I need some sort of m dot. So I'm going to go with 1 kilogram per second. Okay, sure. There is the maximum pressure in the system. I call it P high, basically. P high was supposed to be 15 megapascal, so I got to do everything in kPa, so that would be 15,000 kPa. And there's the low pressure in the system, in the condenser, which was 10 kPa, and of course I keep it as 10 kPa. There was T3, T maximum in the system, I call it T high, and T high was supposed to be from the 600 Celsius, okay? My unit system is Celsius, so it should be good to go. And what else is given in this problem? Okay, well, the quality in the condenser was given. The quality in the condenser was given as X condenser, that's the quality, was given as 0.89, it was 10.4%, so it becomes 0.896. Basically, that would be the quality in the condenser. I have 4 pieces of information, P high, P low, and T high, and X in the condenser. I can solve this cycle. So if you have seen my other videos, every block of the code that I write, basically I just solve it. I just solve it to check the units to see if there is no unit issues with my solution. That's very important that you double check that, because if this as your method that you don't see any unit problems, basically that makes debugging the code when you encounter any error way better, but faster, basically, because you always know that the error is in the last, line of the code. So the first is good. You can save it and keep going. Now we can actually go to states. I can define every state. Let's do the states. So the first state that I need to deal with, I showed you, that's the pump right before the pump. So I know quality 1 is basically 0. Okay, what else did I know about 1? P1, I knew P1 was supposed to be 10 kPa, so I don't need to write it. I just call it P low because I had it up there, so I can, change those values. So because I have these two, independent intensive properties, I can find other properties. I can find S1, right? So S1 would be basically the entropy of water or steam, you can call it steam, that when P is basically P1 and quality is X1, that's it. And if you need to find T1, which in this case we don't, but I mean, because EES can give you everything, I can just, find the lattice right temperature, Control C, and then Control V here, and I have state 1. State 1 is determined. We're good to go. What do? Usually I run it. So I run it to see what do I have here. So I have some unit problems. It's in the array table. I know what's going on. I bring the array table out, and I can fix the units in array table, basically. So I have the value of array table. You can, so T temperature is supposed to be units, right? And this is kilojoules per kilogram Kelvin. If it gives me an error, I can do Celsius and basically fool it, but this is kPa. So now let's run one more time, make sure that there's no unit problems. No, there's no unit problems. Kilojoules per kilogram Kelvin. I can make this look like this so we can see basically everything and there's no unit problem. Now let's go back to the code and keep going. You can save it and keep going. You see how fast this is. That was state 1. Now let's do state 2. State 2, there are 2 ways to solve this. If you remember, I said you can go by, S2 is S1, the whole thing, or you can do, because by hand, H2 would be H1 plus V1 times delta B, because EES does it for me, I don't have to do this. So what properties do I have? I know S2 is supposed to be S1, that's one thing, and P2 was given. P2 was given as the high pressure in the cycle, basically. So I have these two. So I don't have to worry about anything else. Then I can find the value of H2. Oh, I need one H1. Oh, I forgot that one. Let's add that one. H1 is basically the enthalpy of, I can just copy, Control C and Control V, paste. Now it's good. P2 is P high. That's good. Now I can find other things. What do I need? I need H2. H2 is enthalpy of steam. Okay, sure. And when P is basically P2 and S is S2. I got it. And do I need other things? Reality is that I don't need T2 if you want to, and T2 is pretty much T1 because it's liquid water, but sure. I mean, whatever. Temperature, sure. I can just copy this, Control C, and then Control V. I got it. Not a problem. S2 is S1, S, P, H, T, 4 things that I usually need. I have them. What do? You save it, you run it, you make sure there's no unit problem. I know where the unit problem is because I added basically enthalpy, and I need to add the unit for it. So that'd be kilojoules per kilogram. So now we shouldn't have any unit problems, and we don't. That's good. So everything looks nice and clear and good. Okay. So, and you can see that T2 and T1 are pretty close. Why? Because it's liquid water. So it's different when it becomes, superheated. Okay, state 3. State 3, what do I know about state 3? State 3, what was given was that basically T3 is that the T high value, and P3 was that P high value. Okay, and then PO high, what is that? So I got it. Now I need to find 2 other properties. I need S3 is the entropy of steam, right? Steam and water are the same things in EES, by the way. When P is P3 and T is T3. right? And I need H3. H3 is the enthalpy of, I'm going to copy this, Control C, and Control V. Done. TPSH. I got those 4 things that I wanted. What do? Usually you save it, you run it, and you look at your array table, see what's going on with your array table. The array table is good to go. I don't need to find the quality over there. So I have these 4 values. Everything looks pretty good. Now, what we said about state 4, if you remember, I hope that you took a screenshot of the whole problem, so you know what state 4 was. State 4, the only thing about state 4, I have the problem in front of me. So what do I have about state 4? If you remember, is the big deal. If I want to share it one more time real quick, is this was the problem, and so state 4 is right after the high pressure turbine. The biggest deal here was that S4 is supposed to be S3, but I don't know anything else pretty much. And I know P4 is supposed to be P5. Okay, cool. And I know S5 is supposed to be S6, but I don't know anything else. And I need to kind of back solve it from state 6 to state 5 to state 4. So just a quick reminder, let's go back to EES and kind of back solve it. But the information that you have first, you write it anyway. So state 4, what do I know about state 4? I know that S4 is supposed to be S3. I got that, but that's not enough. I'm looking for expression. So let's go to state 5. State 5, what do I know about state 5? State 5, I know 2 things basically. I know that S5 is supposed to be S6, but I'm not going to write it here. The reason is that I don't have S6. So, and I know P5 is P4, but I don't have P4. So let's just wait. Let's go to state 6 first. So because right now everything is known in this code. So if I run it, I'm not going to get any error message. So let's make sure that we don't have any error messages in these. That's a very big deal, and all the units need to be correct. No unit problems must be detected. No unit problem. So state 6, in fact, I know stuff. For state 6, I know X6 is supposed to be the X of the condenser. Whatever I put at the beginning of the code up there, this thing that I put at the beginning of the code here, you see that? So X6 is that, and P6 is that P low in the condenser, what I called as P low at the beginning of my code. That's why I put those values there, so you can play with them here. So now I can find other things. I can find basically H6, right? So H6 is basically the enthalpy of steam, right? And when, I don't know, P is basically P6 and quality is X6, like this. Okay, so I took care of that. And do I need to find T6? Well, T6 and T1 are going to be the same, but sure, I do it, temperature, and that's not a big deal. And Control C, Control V, and done, right? So I have the value of H6 and T6. What do? You run it. You take a look at your array table to make sure that everything is good to go. And so S, oh, I don't see H. Okay, all right. Oh, wait. There you go. Now you're talking. So now I have all these problems. I have the temperature. And if you look at these 2 temperatures, they are the same, right? So this temperature and that temperature are they're supposed to be the same. If you find something else, it's wrong. And so it's good now. I don't know P4 and P5. I'm going to look for that. And as I told you before, it has to be somewhere between 4 to 5 megapascals. That's the rule of thumb about the reheat. High pressure, low pressure turbine. Okay. So now I can go and back solve it. How do I back solve it? I can go to, that's the good thing about EES. I can go back and I can tell state 5, hey, dude, state 5, listen, S5 is supposed to be S6 that I just found. So I have my S5. And what else do I know about S5? The other thing that I knew about S5 was the fact that T5 was T3. That was the deal. It was supposed to be the same as T5. T5 was supposed to be T3 because, it was supposed to be a perfect ideal cycle. So when you reheat it, you manage to reheat it back to the same maximum temperature in the boiler, and of course at a lower pressure, but the maximum temperature. So it's a perfect heat exchanger. Now I have two independent properties at 5. Now I can find its pressure. And I know it's going to be superheated, something, because if it's not superheated, it's not going to go through a turbine. Because if the steam is not superheated vapor, you can't get work, send it through a turbine to generate work, right? So I know this is going to be superheated. So what else do I need to find? I need to find H and pressure. Okay, H5 is basically the enthalpy of steam, like this. And when S is S5 and T is T5, like this. And this is what we were looking for, P5. P5 is supposed to be also P4. Is the pressure. I can copy and paste this. Control C and Control V. I got it. State 5 is determined. Problem is pretty much solved. So now I can go back to state 4 and tell state 4 P4 is supposed to be P5. Now I have two independent properties at state 4. Now I can find other things at state 4. H4 is enthalpy, steam, like this, right? When pressure is P4 and entropy is S4, like this. Of course, if you're looking for temperature, okay, sure, temperature 4 is basically temperature. And of course, you can copy, Control C and Control V here. Now all the states 1 through 6, everything is determined. That's the beauty of it. So I do have everything. State 6, if you need to find entropy at state 6, basically, oh, looks like I forgot to do that. So I need to find S6 before I go up. So good thing I didn't run it. So you need to add this line to your code. Entropy of steam, Control C, and now the code works, basically. So now that we have this code, you can, if you want, you can pause the video and take a look at all these things and make sure that your code looks like this. Let's save it and then run and see if there's no error in it. So let's do that. Looks like there is no error. I got away with everything, basically, and I got these properties. So now you can actually double check your values to make sure that these values are correct, and they can pause the video, double check these values to see if you got these values, then you should be good to go, basically. Our thing was we were looking for P4. Let's see what we got, the mid pressure, right? P4 is 4.014 megapascals. That's what I told you. It's going to be somewhere between 4 to 5 megapascals. A quarter of the maximum pressure, usually that's where the cycle becomes more efficient. I didn't expect it to be 1 megapascal. It's not exactly a quarter, but that's a rule of thumb that it's going to be somewhere in that area, right? So we got about 4 megapascals here, or 4,014 kilopascals here. So we got our answer. We were looking for that mid pressure. We got it. 4 megapascals, 4.014 megapascals. In fact, that's what we got. Now, our next step is to solve the cycle. You can save your code. And the next step is to basically just apply the first law for processes to find the work of the turbine. You have 2 turbines and you have one pump and you have a boiler. So you have to apply the first law for these cases. And so Q dot of boiler, you can just apply the first law of thermodynamics, which I have a separate video about the first law of thermodynamics. In fact, that's the first video I posted on this YouTube channel. You can watch that. That's like 2 hours, whatever. That explains how the first law of thermodynamics works. So if you're not familiar with that, you can watch that video and learn about the first law of thermodynamics. For the boiler, here's the deal. Boiler. We write the first law as Q dot B. Now, I wrote the equations already for you, so I'm going to just apply that. Whatever these streams are going plus m dot, there is no w dot in the boiler. M dot times all the streams that are going in come first, so H2 is going in. What else is going in? H4 is going in. What is coming out? Minus H3 is coming out. What else is coming out? H5 is coming out. H5 equals 0. This 0 has a unit, it's kilowatts also, because the unit of this equation is kilowatts, because I used m dot. M dot is kilograms per second, right? So I got the Q dot of boiler. I can actually, run this code and see what I get for Q dot of boiler. I get 3896 kilowatts. Okay, so the units are fine. Everything is good to go. Let's go back and get stuff done. We do this for the turbines also. Turbines. For turbines, there is no Q dot of turbine because the turbines are isentropic. Negative W dot of turbine total, like this, both of them, that's what I mean, plus M dot times first the streams that go into our system, the way that I picked the system. You remember how I picked the system? I drew a system around both turbines, and I looked at the streams that are crossing the boundaries. So what I see here is the streams that are crossing the boundaries for my turbines is H3 is going in. What else is going in? I see H5 is going in. Okay, what else is going out? H4 is coming out of my system, and H6 is coming out. And the ones that are coming out are negative. The ones that are going in are positive. No, ignore the potential and kinetic energy. They're fine. Equals 0. 0 means steady state. Kilowatts. Okay, I got it. And finally, for the pump, because we have only one pump, it's actually the easiest part. Q dot of pump doesn't exist here because the pump is isentropic, so it's adiabatic. Negative W dot of pump in this case, plus M dot times what stream is going in. Stream that's going in is M dot H1, and what stream is coming out is M dot H2, basically. So that's why I factored out M dot. So H1 minus H2 equals 0 kilowatts, basically like this. So I should have these three, and let's just run the code and see what we get. So it looks like I made a mistake somewhere. Function does not define. What mistake did? Oh, because I didn't put the. Okay. All right, sure. I guess now this, okay. All right, cool. So now we have the total value of work. As I told you before, the W dot of pump turns out to be negative because it's consuming power. Now I have everything to calculate the efficiency of this cycle. So I can go back to my code and do that. So to calculate the thermal efficiency of this cycle, this is how you do it. So W dot net I have to calculate. As I told you before, W dot net is the W dot of turbine, the total value, which is a positive number. You can even add up the W dot of pump because it's already negative. It's going to get subtracted anyways, but just to be consistent with what I showed you, so I use the absolute sign, absolute W dot of pump. That it would be W dot net in this case. I got to call it W dot net to make sure that it's good. And Q dot of boiler I already have, so everything should be good to go. So eta, the thermal efficiency, would be W dot net over Q dot boiler. Done. This concludes our code, basically. Again, I made a mistake. What did I do? Let's see, W dot, I call it W dot T total. So make sure that everything is okay. There you go. So this is the efficiency of the cycle. I got 45%, 0.4499 is 45%. And I got the value of W dot net seems to be 1753 kilowatts per, or you can call it 1753 kilojoules per unit kilogram because I use 1 kilogram per second for M dot. But because I use kilogram per second, my units become kilowatts basically, because all the enthalpies are kilojoules. Now the problem is solved. This is the final solution for this problem. So if you want, you can pause your video and look at all these numbers and all these enthalpies and entropies and everything to see if you got the right values that I got. As a double check, we can also check the solution from the book. So I can share the book for you and see what the book actually got us. So what I'm going to do is I'm going to share the book for you and to see if we are on the right track and we got the same numbers. So let's take a look at the book, see what the book got. Here's the book. The book, this is the problem. The simple ideal, example 10-4 I talked about, you can find it in Thermodynamics book. They use the tables, the steam tables, and so if you want to learn how to do it by hand, although I explain how to find, the stuff. This is the method that you're going to use. But we want to double check our answers. Our answers using EES are more accurate, basically, because it's EES. And let's take a look at this. Looks like we found that pressure to be 4.014 megapascals. And, because there is no table for 4.014 megapascal, what they did here, they just said, okay, it's 4 megapascals, which is a pretty good approximation. I mean, it's just not a bad deal. And then eventually, you look at the whole solution in the book, and I assume that you have the book when you're watching this. And let's take a look at the values that we got. For example, for the Q dot of boiler, I got 3896 kilowatts for 1 kilogram per second. This is 3897, same value that I got because they did it per unit kilogram. I picked 1 kilogram per second, so I get the same values. And for the net amount of work, the value of the pump, I got 15.1. Same case, kilojoules per kilogram, or in my case, kilowatts. And for the W naught net, they didn't do W net. Because it was an ideal cycle, they could use this equation. And in my previous video, I also said the same thing. That the reason that they can use this equation, and still okay, you can't use this equation when the cycle is not ideal. Not ideal means that you have entropy generation and you have head loss and even heat loss in the piping and in the boiler and in the condenser and pressure loss, these things. Then this equation that you see here that they use 1 minus Q out over Q in, that doesn't work. That only works if the cycle is ideal and reversible and the whole thing. The pumps are isentropic, no pressure loss in the boiler and condenser, none of that. But turbines are isentropic also, then you can use this equation. And there's no heat loss in the piping, right? And no pressure loss in the pipe. Then this equation works. If not, the method that I used for you as W dot net over Q dot of boiler, that is the basic definition of the efficiency. So you should use what I showed you. That always delivers the correct efficiency of the cycle. This thing that you see here only works for ideal cycles. So if the cycle is not ideal, do not use this, okay? Keep that in mind. But by checking this number, you can see that they got 45% and we got 45%. So I don't know if no, they did not. They did not calculate W net in this case. They just went with this equation. So this is it. And I hope you learned something from this video. And so if you have any comments, make sure you make comments. I read the comments. And that's it. So you have a wonderful day. Again, one more time, I hope that you learned something from this video and it added some value. Bye-bye.